So before we go into the system level parameters and specification of a amplifier, RF amplifier, the basic building block of an amplifier, we will take a look at it. And in essence, it's essentially a transistor that is going to be amplifying the input signal to achieve a certain RF output, certain RF output power. So apart from the transistor, there is going to be an input matching network and an output matching network that is going to achieve the so-called conjugate match for the input and the output load to transform the load impedance such that it becomes the complex conjugate of the load impedance, looking in impedance into the transistor, and similarly the source impedance is going to be transformed to its conjugate in such a manner that the looking in impedance is going to be the conjugate of the input impedance of the amplifier. But within the amplifier itself, the key element is going to be a transistor that is going to convert the input RF power into a certain output RF power, which is higher than the input. And the extra power that is needed, the output is able to have a higher power from it's essentially converting the DC power. There is a DC power that is being utilized to convert the input power to boost it up to a certain output power. So to understand roughly the consequences of using a transistor in an amplifier, a best configuration to take a look at is the common emitter configuration of a transistor as an amplifier. You know that a BJT, a bipolar junction transistor with a base, an emitter and a collector, a three-terminal device. We know that the collector current is always is going to be the device can be used as a current amplifier, with the collector current being a factor times the base current, and typically the current gain beta that you see here is in the order of 100. So this current gain feature of an amplifier of a BJT transistor can be used so that it can be used for a power amplifier application. So you can see here that what IB is in the base current is going to be around, let's say, 46 microamperes. It's an order of microamperes, but the corresponding collector current is going to be in the order of milliamperes. And in the common emitter configuration, if this collector current flows along this resistor here, there is going to be a resistance, a potential drop between the bias point and here, and the output is essentially the supply voltage minus the drop along that resistor there. So this supply voltage is going to be providing what is called as the DC bias for this amplifier through this kind of a resistive divider network, which sets the base current when there is no RF signal, when the amplitude of the input signal is 0. What should be the base current that is being flowing in is being determined by these resistors here. If you were to look at the so-called output characteristics of a BJT transistor, typically we are looking at the collector current for various collector emitter voltages, for the various voltages across the collector and the emitter, and that is a set of curves that changes for different values of the base current, Through this kind of a bias network, all that we are able to do then is to identify a Q point which is determined by the bias network on the load line, and in essence, whenever there is a change in the base current, we are going to switch on to the different set of base current curves here, and projecting that to the DC load line, we will be able to see what is the corresponding collector current that flows through. So this is going to be the RF signal. When there is no RF signal, essentially when there is no RF signal, that means the base current is maintained at 46 microamperes. The output collector current is going to be simply this value here, which is 4.8 milliamperes. So when the base current increases correspondingly from the load line, which we can see what is the corresponding collector current here. So important thing to note is when the base current goes and exceeds beyond a certain point, if the amplitude of the base current is beyond a certain point, let's say a wider swing of that sort, turns out that the transistor might go into the saturation region, or when the amplitude is so low that it can go into the so-called cutoff region, where the IC turns out to be max out, and there's a minimum value of IC beyond which the collector current can't exceed, or below which it can't go. The output collector current, where for such a wide swing of base current, is going to get saturated and clipped off rather than maintaining a pure sinusoid. And similarly, at the lower swing, it's going to get clipped off when the transistor goes into cutoff. So the output voltage is no more beta times V in. This is only in the ideal case for very low values of the input voltage swing. For very low values of the input voltage swing. If the input voltage swing is the amplitude is too high, then the transistor will either go into saturation or cut off, and it's no more a linear relationship exists. And that's what we're going to see next about non-linearities. That is going to lead into non-linearities, which will be seen in the next video.